Hello, this lecture is on data acquisition for the course ME391, Measurements and Instrumentation. Sensors to measure variables like temperature, pressure, and strain are an essential part of a measurement system. Later lectures will provide a comprehensive coverage of the sensors available for measuring a range of physical variables. Although it's possible to use oscilloscopes or multimeters to monitor these variables, it is usually preferable to use a personal computer to view and record the data through the use of a data acquisition device, typically called a DAQ, D-A-Q. This is a specialized card within the PC or a USB-based device external to the PC. One particular advantage of using PCs in this respect is that data can easily be stored and converted to a format that can be used by spreadsheets, such as Microsoft Excel, or other software packages such as MATLAB. Another advantage is that significant digital processing of the data can be performed in real time via the same platform that is used to acquire the data. This can significantly improve the process of performing an experiment by making the real-time data interpretable and useful for subsequent actions. For example, decisions that have to be made on the basis of the acquired data. Another advantage is accessibility. Data logging devices can be sent to places that humans cannot easily get to. For example, the planet Mars, think Perseverance rover, or to the bottom of a volcano. DAQs also have less human error, have less errors than humans. Humans typically get tired, they write things down backwards, etc. It can also collect data faster. It can write data directly to computer files, and it can collect data 24/7. And lastly, graphs of tables of results can be produced automatically by the data logging software. Disadvantages: the main disadvantage of using a DAQ is the initial cost of purchasing the equipment. While a thermometer can be purchased for less than $1, the price of the components of the data logging system to record the temperature would be considerable. It is a prerequisite of DAQs that the measurement system is designed to maximize the quality of sensor outputs and minimize the occurrence of systemic error, as will be discussed in a future lecture. However, it is usually impossible to eliminate all errors and is often difficult to achieve sensor outputs of a suitable amplitude. Thus, in general, signals acquired via sensors must be processed or conditioned to make them suitable for subsequent analysis or for integration within control loops. Since signals acquired via common sensors are often analog, that is, continuous in time and in a range of values, some level of analog signal processing is generally required. Now, the purpose of signal conditioning is threefold. It's to amplify weak sensor signals. It's to filter the inherent noise that is usually mixed in with the original signal, and to eliminate high-frequency components in the signal that would cause aliasing. That is, presence of dubious counterparts of the original signal when sampled below a certain sampling rate, commonly referred to as the Nyquist rate. That's Nyquist. Signal processing is also usually necessary to deal with induced noise that arises when signals are transmitted from sensors to other parts of the measuring system, even when efforts have been made to minimize the magnitude of this induced noise as much as possible. Analog signal processing is therefore essential to the processing of DAQ data, even if one is largely reliant on a digital computer-based system. With this in mind, we shall initially consider the essential aspects of analog signal processing with a view towards these techniques that are meant to address the three aforementioned concerns: amplification, filtering, and anti-aliasing. With the above in mind, the following basic concepts are discussed in the current lecture: DAQ process and its components, and aliasing phenomenon, Nyquist frequency and Nyquist rate. You should be able to understand the basic processes that are required in transforming a sensor signal from its raw form into a form that is suitable for subsequent analysis in a digital computer. Now, data acquisition is the process of collecting and measuring signals and sending them to a computer for processing. DAC systems capture, measure, and analyze physical phenomenon from the real world. Light, photocell, temperature, thermocouple, motion, encoder, fluid flow, impeller, and pressure are examples of the different types of physical phenomenon that a DAC system can measure. The building blocks of a DAC system include the very first thing is, of course, the physical system itself, right? There's going to be something we're measuring, and that something we're measuring is called the measurand, M-E-S-U-R-E-A-N-D, measurand, and it's the variable that we're measuring. Now, the transducer is a device that converts a physical phenomenon such as light, temperature, or pressure, or sound into a measurable electrical signal, such as voltage or current. The signal is the output of the transducer, and it can be noisy. Signal conditioning is circuitry to make the signal suitable for measurement, or to improve the accuracy, or to reduce noise. These include things such as amplification and low and high pass band filters. And next we have A to D converters. This converts the analog signal into a digital signal. And finally, we have the computer and application software, which help you easily design and program your measurement and control application. In general, signals are acquired from sensors are either weak and small in magnitude, or contaminated with noise, or both. For instance, the original voltage readings generated by a thermocouple is in the range of microvolts, making it difficult to process via a DAC system without appropriate amplification and other types of preconditioning. Similarly, the signal generated by an accelerometer is typically very noisy as it is. And here in this graph, these three graphs, we see the output from a 3-axis accelerometer attached to a stationary object. It shows variations that are quite consistent with the nature of this type of measurement. The expected signal is constant, and all the variations are, in this case, due to sensor noise. The so-called spectrum of this type of noise is often wide, necessitating preconditioning the signal using an analog filter prior to acquisition with a digital DAC. This has to do with the so-called aliasing effect that can seriously undermine any digital signal processing system if it is not properly sampled. In general, aliasing occurs if the bandwidth of the analog signal that is being sampled by the system at discrete intervals exceeds the so-called Nyquist frequency. When a high-frequency signal is sampled by a computer DAC, only a limited amount of information is captured, once per sample. If this sampling rate is high, sufficiently high, the loss of fidelity is not significant. However, as the sampling rate is reduced, the signal looks less and less like the original. This is depicted, as you see here, where a sinusoidal function of 1 Hertz is sampled initially here at 50 samples per second, here sampled at 5 samples per second, and lastly at 2 samples per second. Clearly, the discretized representation of the original analog signal is very realistic at high sampling rates and degrades perceptibly as the sampling rate is reduced. Now, the Nyquist rate of a band-limited signal is twice the maximum frequency of that signal. In more specific terms, a signal that is sampled at a rate that is below its Nyquist rate will appear to include low-frequency aliases of the high-frequency components that are contained in the original signal. So basically, you need to sample at twice the highest frequency in your signal. So you need to know the frequency components of your signal, and you can use Fourier transforms for that. But whatever the highest frequency component that you want to measure, you need to sample it at least twice the rate. That's what this 2 is, twice the signal. So for example, audio CDs, if you remember those, maybe not, but they were sampled at a certain rate. And how fast should they sample the sound? right? That's the question. How fast should the CD, I mean the digital conversion of analog sound into digital sound, how fast should it analyze, a music, a sound? Well, humans can hear typically up to 20,000 hertz, right? Well, twice that is 40,000 hertz. So you would need to sample music at least 40,000 hertz in order to capture the signal in true form so that it sounds right. And in fact, CDs are sampled at 44,000 hertz per second. I'm sorry, 44,000 samples per second. Okay, let's move on here. Also in the lab, you're going to be using a function generator, and these are used to generate signals for testing and operation of equipment. So basically, I'm going to just run this.
What is a function generator? A function generator generates waveforms. A typical function generator will let you generate sine waves, square waves, and triangle waves. Some really expensive function generators, called arbitrary waveform generators, will allow you to generate any waveform you want with any shape you want. To use one, you must first connect some wires to the BNC jack labeled 50 ohms. I'm going to use an oscilloscope probe here because I found that they work really well for this sort of thing. The voltage waveform will appear on the probe's tip. Now you can switch between waveforms at the push of a button. Changing the frequency of the waveform is easy too. Just use this dial and the appropriate frequency range buttons. You can also change the amplitude of the wave. And you can give it a DC offset like this. Now let's look at duty cycles. The duty cycle of a wave is basically the percentage of the time that the wave stays at the higher voltage. I can change the duty cycle using the symmetry dial over here. So what's the real-world application of all of this? Well, basically, the function generator saves you the time and hassle of having to build oscillators when you're prototyping a circuit. Let's run through a real-world example where we make an LED dimming circuit. I have a transistor here, a power supply set to 12 volts, and a bunch of LEDs. By connecting the function generator's output to the base of the transistor, I can switch the transistor on and off, which will turn the LEDs on and off. Now I have to use a transistor here because a function generator on its own isn't powerful enough to power anything. By changing the frequency of the wave, I can change the rate that the LEDs blink. Let's make it so the LEDs are blinking so fast that our eyes can't see it anymore. It turns out that this happens at around 1000 Hz. By changing the duty cycle of the wave, I can change the brightness of the LEDs because they're only on for a certain percentage of the time. So now I know that when I'm finalizing my dimmer, I should build an oscillator that puts out a waveform that's at least 1000 Hz. You can also use a function generator to prototype audio circuits, low-pass and high-pass filters, and much more. You can get a function generator off of eBay for about $100. They're all pretty much the same, and the main thing you need to worry about is the maximum frequency that they can output. My generator only goes up to 2 MHz, but if you're willing to spend the cash, you can get a generator that'll create signals up to 50 MHz and beyond. Thank you for watching this tutorial, and I hope you enjoyed learning about function generators.
Now, moving on to oscilloscopes, they're used to measure signals. The x-axis is time, right? That's this x-axis on the screen here, time, it's usually. And the y-axis is DC volts. One can vary the scale on either axis using these knobs over here. Most oscilloscopes can read multiple channels at once and can store the data on a computer. So I'm going to show you 3 videos on the use of oscilloscopes.
First part in a multi-part series of videos about oscilloscopes. In this first video, we're going to answer these questions. Oscilloscopes, what are they? Why would I need one? Which one do I get, and where do I get one? First question, what's an oscilloscope? An oscilloscope is a device that lets you view changes in voltage over time. Volts go on the vertical axis and time goes on the horizontal axis. You can change the scales of the axes to measure tiny signals or large signals, fast-moving signals or slower signals. So why would you need an oscilloscope? Well, let's say you're trying to build a dimmer circuit for your headlights, and you need to see if it's going to work first before you hook it up to your car. An oscilloscope can show you whether the circuit is behaving correctly or if you need to fix something. Or let's say you're trying to build one of those headphone amplifiers that fit in an Altoids tin. Don't you want to make sure that your circuit is working right before you hook it up to your $200 headphones? Basically, trying to analyze a circuit without an oscilloscope is like trying to paint a picture without your eyesight. The oscilloscope allows you to fix small problems before they become big, expensive problems. And if you're serious about your electronics hobby, you need an oscilloscope. So, which oscilloscope do you get, and where do you get one? Well, brand new oscilloscopes are normally really expensive, reaching into the $1,000 range. But if you buy a used scope, you can get one for a couple $100. Now, to give you an example, I have never paid more than $400 for an oscilloscope ever. So, let's go on to eBay now and see what options you've got. Search for oscilloscope. You're going to see a lot of scopes here with bandwidth numbers. Now, I'd recommend getting one with at least 10 MHz bandwidth, but don't bother with anything higher than 100 MHz because you're never really going to need it. If you see scopes listed with megasample ratings, 100 megasamples per second or higher is good. Don't worry so much if you don't understand what those mean just yet. Once you've used your oscilloscope for a while, it'll become clear. Now, in terms of brand names, the best oscilloscopes you can get are HP, Tektronix, and Agilent. So the next question, do you get an analog scope or do you get a digital scope? You can save some money by getting an older analog scope, and that might be all you need if all you're working with is analog circuits. However, a digital scope will have some nice advantages, such as being able to measure voltage and frequency for you, and it'll allow you to save waveforms to analyze later. Now, if you ever intend to work with microcontrollers or serial communications, I highly recommend a digital oscilloscope. Nowadays, you can also get cheap USB-based scopes that you can plug into your laptop. Generally speaking, I stay away from these just because in case you connect something wrong, you don't want to risk frying your laptop. Also, standalone oscilloscopes tend to have higher ranges of voltages that you can measure. Now, I'd only get a USB scope if you seriously cannot afford a better standalone scope. A one-channel oscilloscope is okay, but if you can afford it, I'd highly recommend getting a two-channel one simply because it's going to make comparing waveforms so much easier. And a four-channel oscilloscope is probably overkill for your first time. Finally, use your common sense. This is eBay, so don't buy an oscilloscope that's listed as untested or as is. Make sure that you see a listing with a picture of the scope, powered on, and measuring something useful. It's not always necessary to have a scope that's precisely calibrated, but if you can get one for cheap, then go for it. Now, if you don't want to bother with eBay, you can actually get a brand new oscilloscope for cheap. This is the scope I just bought, $325 brand new from Salig.com, and they even shipped it to Canada for me. As you can see, it works just fine. Alright, so now that you've got an oscilloscope, check out my next video showing you how to use it. This is the second part of my oscilloscope tutorial showing you how to measure stuff with an oscilloscope. The first thing you're going to have to play with is your oscilloscope probe. You should have gotten one with your oscilloscope, but if you didn't, you can get one for $10 from mpja.com. All oscilloscope probes will have a little attenuation switch where you can set them to X1 or X10 attenuation. 99% of the time, you just want to leave it set to X1. The X10 setting just divides the signal by 10, which you usually don't want to happen unless you're working with high voltages. The oscilloscope probe will have a BNC plug on the back that you plug into the scope, like this. Once that's done, you don't need to unplug it again. The probe will have two main parts, the ground clip and the tip. The ground clip is just a little alligator clip that you're supposed to attach to the circuit ground or circuit common. If you don't know what that means, just connect the ground clip to the negative terminal of your battery. Now, the other important part is the probe's tip. When you want to measure the voltage in the circuit, you touch the tip of the probe to the part of the circuit you want to observe. You can also use these probe clippy things to grab wires in the circuit, leaving your hands free to do other stuff. Now, I'm going to connect my probe to a signal generator so I can show you some nice easy examples. So now that you have your probe clipped onto a part of your circuit, you should see some sort of signal on the screen. Now let me explain what you're seeing. The screen is evenly divided up into little squares or divisions. Each division represents a certain number of volts on the vertical axis. On the horizontal axis, each division represents a certain number of milliseconds or microseconds. Right now I have things set up to be 1 volt per division and 1 second per division, for the sake of simplicity. Now, as you can see, it's not so easy to see what's happening in this signal, so we want to sort of zoom in and out. Now, we do this by changing the volts per division and the seconds per division. The exact setting you will use will depend on the signal you're viewing and your personal preferences. And there's no harm with messing with these settings, so you can zoom in and out all you want until you get a good feel for what's happening. Also, you can use these little positioning knobs to move the waveform up and down so it fits nicely on your screen. The next thing I want to talk about is DC coupling, AC coupling, and ground coupling. All oscilloscopes will allow you to choose between these modes. DC coupling is generally what you want to use for most circuits because it'll allow you to view most DC voltages. For the sake of example here, I'm going to hook up my probe to a 9-volt battery. You can see how the line jumped up to show the presence of a DC voltage. If we count the number of vertical divisions, we can see that the voltage being shown is roughly 9 volts. Also, since I have a digital oscilloscope, I can see that it's doing the measurement for me. However, sometimes you might want to ignore the DC component of a signal and only focus on the small AC variations. An example of this is if you're trying to discover if your circuit has a nicely filtered power supply. So let's look at my simulated example. Over here you can see a power supply that looks like it's 5 volts. But if I set my scope to AC coupling and zoom in, I can see that in fact there are some tiny AC voltage variations laid on top of the DC signal. Now according to the display, each division is representing 100 millivolts, so the AC ripple of this signal is approximately 100 millivolts from peak to peak. Now 100 millivolts is fine, that's only 2% of the DC voltage of 5 volts. But if you ever run into a DC power supply with several volts AC on it, you know that something is screwed up and you gotta fix it. Now remember the final type of coupling I talked about? Ground coupling? That basically just means that you aren't measuring anything at all. You're just measuring ground. In other words, it's kind of a useless setting, and the only time you ever use it is when you want to reposition your waveform to represent 0 volts right in the middle of the screen. Finally, I want to show you a real-world example on this headphone amplifier I built. You can see that when I crank up the volume, I'm getting massive fluctuations in the power supply voltages. So, what's the solution? I have to add some capacitors to smooth out that voltage. Now here's what it looks like after the capacitors are installed. Much better. And the sound will be better too. So that's 99% of what you will ever need to know about oscilloscopes. Now if you want to become an expert, check out the next episode where I'll talk about some of the more advanced functionality of oscilloscopes. This is the final part in my oscilloscope tutorial trilogy. The first thing I want to talk about is triggers. What is a trigger? A trigger is a voltage threshold that the signal has to reach before it gets displayed on screen. Now let me give you an example. By default, your oscilloscope is probably set to automatically trigger on whatever looks like an interesting waveform. This works really well for repetitive signals like the sinusoid I'm viewing here. But what if I'm trying to observe serial data? Serial data can come and go in the blink of an eye. If someone types a character on a terminal, that character will get transmitted in about a millisecond, and unless you have the right trigger settings, you might miss it. Now let's try that again with some different trigger settings. Here I have my oscilloscope probe stuck right into the transmit pin of an RS-232 port. Whenever I type a character on HyperTerminal, I want the raw bits to get captured and displayed on screen. If I go into the trigger menu, I can see some options for slope and mode that I want to change. Changing the slope means that I can set the trigger to fire on a rising edge, meaning a transition from a low voltage to a high voltage, or a falling edge, meaning a high voltage going down to a lower voltage. With the mode setting, auto mode is good for repetitive signals, but since we're looking at serial data, we want to use the single setting. This will allow us to capture a single waveform and keep it static on screen. Also, the trigger level knob over here will let me set the trigger threshold, so that when the voltage goes beyond a certain level, the trigger fires and the signal is captured. I'm going to set the trigger to 1 volt now. Alright, let's try this again. Excellent! Now I can clearly see the 1s and 0s on screen, and if you can read binary, you can verify that the correct data is being transmitted. Now this may not seem so useful when I'm using a PC with HyperTerminal and I already know what key I'm typing, but if you're designing something without a screen, this becomes important. The last topic is 2-channel mode and math functions. I can enable the second oscilloscope channel just by going to its menu and turning it on. You can change the volts per division setting of the second channel independently to the first channel. This can let you view the DC and AC parts of a signal at the same time. You can also do fun stuff with the math menu. You can add voltages together or subtract them and get the result displayed as a waveform on screen. Let's say you want to measure the difference between 2 voltages in a circuit. You can use the subtract function to accomplish this. If there's a voltage difference where there shouldn't be one, you might have something wrong in your circuit board. Well, that's the end of the tutorial. Chances are by now you know more about oscilloscopes than your teacher. Have fun!
Now moving on, this is a device we're going to be using in the DQ lab. It's called a thermocouple. And we'll talk more about thermocouples in a later lecture. But just what you need to know, they consist of 2 dissimilar metal wires, so metal A and metal B. They're welded at one end, and they transduce or convert temperature into voltage. And I'll show you this video.
Hi, I'm Bill Griffith, an application engineer with Agilent Technologies. I'd like to do a short tutorial on thermocouples today and talk a little bit about how they work. With me, I have a J-type thermocouple. It's one of the common types of thermocouples. each of the different types of thermocouples are good for different temperature ranges and different applications. They're individually color-coded, so you can determine what type of thermocouple you're using. One of the interesting things about a thermocouple is it actually creates a voltage based on the temperature difference from one end to the other, or what's known as the temperature gradient across the thermocouple. So in order to determine the absolute temperature at the end of our thermocouple, we need to have a temperature reference. So on our data logger cards, we have a built-in temperature reference. So there's a temperature sensor that measures this temperature, and we can measure the voltage of our thermocouple and determine the temperature gradient across the thermocouple. And if we add those two temperatures together, then we can determine the temperature at the end of our thermocouple. So Seebeck observed that in a wire, when it's exposed to a temperature gradient, that actually creates a voltage that's proportional to that temperature gradient. He then determined that it's different for every type of metal, and so our thermocouple is actually made up of two different types of metal, and what we rely on is the difference in voltage that's created when they're both exposed to the same temperature gradient. So to further illustrate this point, if this thermocouple was made up of the same type of wire, we'd end up with two voltages that were equal and opposite, and so we wouldn't have a differential. So it really relies on having the two different types of metal. In addition, the relationship between voltage and temperature is complex. So we can either use a complex polynomial or use tables to look up the voltage to temperature conversion. Lastly, when you add the thermocouple to the temperature reference, you actually introduce a third type of metal and two more dissimilar metal connections. But since the data logger knows the temperature at that point and it knows the type of metals that are being connected, it can actually back out that error. The 34972 and 34970 use what's called a universal channel. So we can connect our temperature sensor to any channel, and then from the front panel we can select the type of temperature sensor we're using, and its built-in algorithms will calculate the temperature at the end of our temperature device. This particular thermocouple, along with a screwdriver, came with our 34972, so it makes it really easy to set up and start making thermocouple measurements with the 34972. If you'd like to learn more about temperature measurements, check out our application note 290 for lots of information on making temperature measurements. Thanks for watching.
Here's some images of thermocouples. You can see one here. It's welded together. And these are more sophisticated. They're enclosed in sheaths to protect the thermocouple, maybe from corrosive elements or high temperature, low temperature, what have you. This is the DAC that we're going to be using in the labs from National Instruments. It can read up to 4 thermocouples at a time. Now, in the DQ lab, you will write a MATLAB program to acquire temperatures from this DAC. Okay, that's it for this lecture. Good luck with the lab, and I'll see you in cyberspace.